full screen is... Yes. Okay, so yeah, thank you very much for this introduction. First of all, I would like to thank the organizers for inviting me to this conference. I'm very happy to be here again. And maybe I will start with a little story, with a little non-scientific story, because this is the Smirnov readings. So actually, the very first international conference at which I gave a talk was the 5th Finnish Soviet Logic Symposium in 1987. And this was a big adventure for me. So I was a young German PhD student accompanying my PhD supervisor, who was an Englishman, to a Finnish Soviet conference. And so at that time I was living in West Berlin, so I had to go to East Berlin, and from there I flew to Helsinki. And the conference started at Georg Henrik von Wright's place. And the other day, the whole conference, after some talks in Helsinki, went on a train and went to Tampere. So this was all very exciting. And at that conference, there was the Soviet delegation, and clearly the head of the delegation was Professor Smirnov. And I remember some other colleagues, Piotr Bistrov, Sasha Karpenko, Ira Gerasimova, and it was a wonderful conference. So I'm really happy to have the opportunity to talk at the Smirnov readings, because I met Professor Smirnov on that occasion. So my talk is on synonymy and proof-theoretic semantics, and actually I want to share some ideas with you. So I'm keen on any critical comments you might have on what I'm going to present. Yes. So there's this area of proof-theoretic semantics. There's a nice survey of it in the Stanford Encyclopedia of Philosophy. And the central concept in this semantic paradigm is the notion of validity, or proof-theoretic validity. So this is the key concept in proof-theoretic semantics. But there are other semantical notions. And there's, for instance, the notion of synonymy. And if you look at the Stanford Encyclopedia article, you will find nothing on synonymy in proof-theoretic semantics because, well, as I said, the focus is on validity. But I think it might be interesting to develop some ideas how to deal with synonymy in proof-theoretic semantics. Now, in linguistics, a distinction is drawn between what's called total and partial or relative synonymy, where total synonymy is a very strict synonymy in a very strict sense of linguistic of sameness in sameness of linguistic meaning in all aspects. Examples of strict synonymy are not so there are not so many examples of strict synonymy. One example that is often given is the expression square and equilateral rectangle. They are sometimes often said to be strict synonyms. There are more examples of partial synonyms, for instance, discover and find, new and novel, buy and purchase. But some linguists doubt that there exists strict synonymy. But even if there's only partial, non-strict synonymy, it is generally agreed that synonymy implies sameness of denotation. So there's a consensus on this, at least. And the reasons for assuming partial instead of strict synonymy in natural languages have, for instance, to do with different connotations or different dialects, but they do not apply to formal languages. I mean, it does not make sense to talk of dialects of first-order languages or so. And in this talk, I want to pursue the idea of explicating synonymy between formulas of a certain formal propositional language in terms of identity between derivations in a given sequence-style proof system, and therefore there's no point in drawing a distinction between strict and partial synonymy. So because formal, this distinction, as it seems, does not apply to formal languages. Okay, so the topic of identity of proofs is around in general or structural proof theory from the very beginning. So there's a seminal paper by Doug Pravitz where he brings up the topic of identity of proofs. And the idea is to look at different proofs of one and the same formula and to wonder when are these different proofs such that one can identify them. So when are the differences between two distinct proofs, here understood as linguistic objects, proof figures or proof trees, of one and the same formula so inessential that it is justified to identify the two proofs? And one can modify this question and ask a question that is in a sense dual to it. But it seems that this question has not very often or maybe never been raised so far. When are the differences between two distinct formulas so inessential that these formulas admit of identical proofs? So, and if these formulas, these possibly distinct formulas admit of identical proofs, then one might think of considering these formulas as synonymous. So this is the idea, and I want to explore this idea in this talk. I think that the question appears to be not unnatural, maybe even natural, if the idea of working with more than one kind of derivations is taken seriously. So if we draw a distinction between proofs and refutations, and proofs and disproofs as primitive entities, then it is quite conceivable that a proof of one formula amounts to disproof of another formula, and vice versa. Okay, but then if a proof of a formula A is identified with a disproof of the negation not A of A, and a disproof of A amounts to a proof of not A, then quite obviously the syntactically distinct formulas A and not A have one and the same proof and one and the same disproof, if they have a proof or disproof at all. So there are two distinct formulas that happen to have the same proof. And well, then it maybe is quite natural to think of these formulas as synonymous if they happen to have identical proofs, and in this case even identical disproofs. So in this context, where one is ready to draw a distinction between different kinds of derivations, especially a distinction between proofs and refutations or proofs and disproofs, then this idea might come up quite naturally. So as I said, once the possibility of identifying proofs and disproofs of distinct formulas is recognized, it may then be used to define a notion of synonymy between formulas. So in here's the idea. Two formulas A and B are synonymous just in case two conditions are satisfied for any finite multisets of assumptions, where assumptions are seen as formulas that are assumed to be true. And so there's a set of assumptions, delta, and a set of counter-assumptions, formulas that are assumed to be false, gamma, and then the two conditions are these. For every proof of A from the set of counter-assumptions gamma and assumptions delta, there exists an identical proof of B from gamma and delta and vice versa. And moreover, for every disproof of A from gamma and delta, there exists an identical disproof of B from gamma and delta and vice versa. And under these conditions, then the idea is these formulas A and B are synonymous. And I want to develop this idea. And the starting point for this endeavor is the Brouwer-Haitink-Kolmogorov or BHK interpretation of the connectives of intersynistic propositional logic in terms of canonical proofs of compound formulas. Good. So if you look into the literature, you can find slightly different versions of this Brouwer-Haitink-Kolmogorov interpretation. And here's one due to Jean-Yves Girard. Girard says, a proof of A and B is a pair PQ consisting of a proof P of A and a proof Q of B. A proof of A or B is a pair IP with I equals 0 and P is a proof of A, or I equals 1 and P is a proof of B. A proof of A implies B is a function f, which maps each proof P of A to a proof f of P of B. And in general, the negation not A is treated as A implies absurdity, where absurdity is a sentence with no possible proof. So this is one version of the BHK interpretation. And according to this version, one and the same construction can be a proof of different formulas, say of A or B and A or C. So if P is a proof of A, then the pair 0P is a proof of both A or B and A or C for any formulas B and C. So Troelstra and Van Dalen regard this Brouwer-Haitink-Kolmogorov interpretation as a very natural semantics for intuitionistic logic, and for Girard, the Haitink semantics of proof even is one of the greatest ideas in logic. But this Brouwer-Haitink-Kolmogorov interpretation has been criticized, and it can be criticized, especially for its treatment of intuitionistic negation. And there's a very interesting paper by Edgar López Escobar, where he suggested to supplement the Brouwer-Haitink-Kolmogorov interpretation of positive intuitionistic logic, where you have this notion of proof or construction, with a primitive second notion of refutation or disproof, to give an interpretation in particular for negation. And what one then obtains is a semantics for David Nelson's four-valued paraconsistent logic with strong negation, nowadays often called N4. And López Escobar gives the following disproof interpretation of the intuitionistic connectives conjunction, disjunction, implication, and this strong negation. So here we have his clauses. So the construction C, he says, refutes A and B if C is of the form of a pair ID, with I either 0 or 1, and if n equals 0, then D refutes A, and if I equals 1, then D refutes B. The construction C refutes A or B if C is of the form of a pair DE, and D refutes A and E refutes B. The construction C refutes A implies B if and only if C is of the form of a pair DE, and D proves A and E refutes B. And this is of particular importance here, the construction C refutes the negation not A if C proves A. So if we look at these clauses, the first three disproof clauses specify the form of canonical refutations of conjunctions, disjunctions, and implications. But the clause for strong negation is different. It gives you, it tells you that a construction C is a refutation of not A, just in case the very same construction C is a proof of A. And moreover, López Escobar requires that a construction C proves the negation not A if C refutes A. So here we do not see a construction as having a certain structure, but one construction, well, does two things simultaneously. It may prove A and refute not A. Good. There's a fundamental assumption underlying López Escobar's approach, namely that for no formula A, there is a construction that both proves and disproves A. If we make an additional assumption, namely that for no formula A, there exists a proof of both A and its strong negation not A, then the ex contradictione quodlibet principle as a formula becomes provable. Now the Brouwer-Haitink-Kolmogorov interpretation is a sound semantics for intuitionistic logic, in the sense that if a formula A is provable in intuitionistic logic, then there is a construction that proves A in the sense of the Brouwer-Haitink-Kolmogorov interpretation. And similarly, Nelson's four-valued logic N4 is sound with respect to López Escobar's proof-disproof interpretation. Good. Now let's look at some sequent calculi for Nelson's four-valued logic. So I will first present a certain standard sequent calculus for Nelson's four-valued logic, and then a modified version of it, which is especially useful for my purposes of coming up with the notion of synonymy between formulas. So the language of this N4, it makes use of certain connectives, implication, conjunction, disjunction, and the strong negation. And I will use lowercase letters to denote prepositional variables, Latin capital letters to denote formulas, Greek capital letters to represent finite, possibly empty multisets of formulas, and I will use some standard abbreviations. In particular, in addition to this biconditional, A if and only if B as an abbreviation of A implies B and B implies A. There is an abbreviation for what is called strong equivalence, which requires that not only A if and only if B, but also not A if and only if not B. An expression then has the form gamma arrow C, so we have single conclusion sequence, and well, a sequent calculus is a non-empty set containing some axiomatic sequence and some sequent rules of the form displayed on the screen. Derivations in the sequent calculus are inductively defined as usual, and so what will play a role is the notion of an admissible rule, and I will make use of this notation here. So if D is the derivation of a sequent S, I often write it in this two-dimensional notation, so that D and D over S stand for the same derivation. So D over S just indicates that the derivation D ends in the sequent S. And a rule is admissible in the sequent calculus if, for any instance of the rule, if the premise sequence are provable in the sequent calculus, then so is the conclusion sequence. Okay, but this is a familiar notion. Good. So as I said, there's a sort of standard sequent calculus for Nelson's four-valued logic, and here the initial sequence or axiomatic sequence come in different form. So we have for propositional variables axiomatic sequence P arrow P, but also not P arrow not P. This is because, well, the truth and falsity are really seen as separate concepts here, and the strong negation expresses falsity. Then there are some standard structural inference rules, cut, weakening, monotonicity, and contraction, and some standard left and right rules for intersynesthetic implication, conjunction, and disjunction. But what is then different from other systems is that there's another set of rules for strongly negated compound formulas. So for strongly negated negations, so there are rules for introducing double negation on the left and the right hand side of the sequent arrow. And there are left and right rules for negated implications, conjunctions, and disjunctions. And the rules are such that they give you all the De Morgan laws and the double negation laws. Okay. What is a drawback maybe of this sequent calculus is that these rules for negated formulas, they may spoil the subformula property. So if you look, for instance, at the rule for introducing negated conjunctions on the right-hand side of the sequent arrow, then the not B in the premise sequence is not a subformula of the negation of A and B. Good. We can obtain the sequent calculus for positive intersynesthetic logic from this sequence system by deleting the initial sequence of the form not P arrow not P, and by deleting all logical inferences that display the strong negation. And then in a paper with Kamide, we gave a syntactic embedding of this sequent calculus for N4 into the sequent calculus for intersynesthetic logic, and we used it to prove that the cut is admissible in cut-free GN4. This is a rather useful observation because from it we may derive that N4 is decidable, that it is really a constructive logic insofar as it not only satisfies the disjunction property but also the constructible falsity property. So if you prove for the negation of A and B, then either negation of A is provable or the negation of B is provable. And it also follows that N4 is a paraconsistent logic so that the strong negation is a paraconsistent negation. Good. So this is the standard sequent calculus for Nelson's this is a sort of standard sequent calculus for Nelson's four-valued logic, but there's also so-called subformula sequent calculus, S and 4, and it makes use of two kinds of sequent arrows, one for proofs, the arrow plus, and one for disproofs or refutations, the arrow minus. And then sequents have this form, gamma colon delta arrow minus A, or gamma colon arrow plus A. And so the gamma is meant to represent counter assumptions, formulas that are assumed to be false, and the delta just contains assumptions. Yes. So these are now two kinds of sequence we use. And the intuition is this sequence of the form A1 to AN, colon, B1 to Bn, arrow plus C. They can be understood in the sequence system for SN4, this subformula sequence calculus. They can be understood as sequence of the form not A and so not A1 and so on, not AM, B1 to Bn, arrow C in GN4. So the counter assumptions can be understood as strongly negated assumptions. And similarly, if we have an arrow minus C sequent, then well, the conclusion C can be understood as being strongly negated in GN4. Good. So here's the sequence calculus. So we have again two kinds of initial sequence. So if P is in assumption position, then we have arrow plus P, and if P is in counter-assumption position, then we have P arrow minus P. And then we have a number of so-called interaction rules. And these are now of interest for me or us, if you listen. So the idea is applications of these interaction rules, they do not affect the identity of derivations. So for instance, if you have a refutation of not A, then if you have a refutation of A, it gives you a proof of not A. So this idea does not have an effect on the identity of the derivation. Or if you have a proof of A, you have a refutation of not A. If from the assumption that A, you have arrow C, then from the counter assumption not A, you have arrow C. So these rules just do not, this is the idea at least, do not affect the identity of derivations. Good. Yes, so these were the interaction rules. And then we have structural rules, and they come now in two versions, depending on whether you consider, when we have these two kinds of sequence. So then we have, yes, contraction minus and contraction plus, for instance, depending on whether the formulas on the left appear in as assumptions or counter-assumptions. And also the logical rules come as positive or negative rules. So if you look at the introductions on the right-hand side of the sequence arrow, so the positive rules introduce introduce into the plus arrows, and the left rules into assumption position. And the negative rules then dually introduce on the left-hand side into counter-assumption position, and on the right-hand side we have the introduction into minus arrow. Into refutations. Good. Then it's not difficult to show that you have this identity axiomatic sequence for arbitrary formulas A. And we can make an observation that justifies the earlier mentioned intended reading of this sequence. Namely, if gamma and delta are finite multisets of formulas and C is a formula, then if in this SN4 system you can prove gamma colon delta arrow plus C, then in GN4 you can prove, well, the negation of gamma means the negation of every element of this multiset delta arrow C. And similarly for these minus sequences. If in SN4 you can prove gamma delta arrow minus C, then in GN4 you can prove this sequence. And if in GN4 without cut you can prove such a sequence, then in SN4 without the two cut rules you can prove this corresponding positive sequence. Whereas when in GN4 without cut you can prove this sequence with a negated conclusion, then in SN4 without the two cut rules you can prove this minus arrow sequence. Good. Now the two cut rules are admissible in cut-free SN4, and then we have the problem that 4 of these interaction rules, they are, if we go back to them, they are subformula property spoiling, because here you derive that you have a disproof of A, but you obtain it from a proof of not A. So if you do bottom-up proof search, this rule is bad because it's you do not have a progression to subformulas. But one can show that, well, so if gamma delta again we find a multi-set of formulas, you see subformula, and then if we consider this system, which is cut-free SN4, where we also remove these subformula spoiling interaction rules, then in GN4 without cut, if there we can prove this sequence, then in the subformula calculus without these subformula spoiling interaction rules, we can prove this the correspondence sequence. And similarly for negated conclusions here and disproofs in SN4 minus. And this allows us to show that the subformula spoiling interaction rules are admissible. Good. So we could do without them in principle. This is nice. So SN4 has the subformula property. Good. So from now on, I will focus on cut-free SN4, and now I will define a notion of identity between derivations in cut-free SN4. And we want to have a notion of identity of derivations such that, for instance, not A and not B and the negation of A or B have identical proofs. Why? Because a proof of not A and not B is an ordered pair consisting of a proof of not A, a disproof of A, and a proof of not B, a disproof of B. Well, yes. And according to Lopez Escobar's proof-disproof interpretation, this is a pair consisting of a disproof of A and a disproof of B, which then is a disproof of A or B, and therefore it's also proof of not A, of the negation of A or B. Yeah. Good. So this is, if our project is inspired by Lopez Escobar's proof-disproof interpretation, then we want to identify a proof of not A and not B, for instance, with a proof of the negation of A or B. Good. So in what follows, I will use this notation to indicate that these two derivations, D and D prime, are literally identical, syntactically identical. And here's the definition. So I first define this relation double tilde between derivations D1 and D2 in cut-free SN4 by saying that D1 and D2 stand in that relation if D1 has this form and D2 has this form. So they start from literally identical derivations, D and D prime, and then we have a chain of application of single premise interaction rules, which do not have an effect on the identity of derivations. That's the idea. Or D1 and D2 have this shape. So we have premise derivations D1 and to Dn, and D1 prime to Dn prime, ending in sequence with the same counter-assumptions and assumptions, but proving or disproving different formulas A and B. Then, these derivations D1 and D2 stand in that relation if the premise derivations Di and Di prime stand in that relation. So this is an inductive definition. And finally, I use this symbol to denote the transitive closure of the double tilde relation. And two derivations D1 and D2 in cut-free SN4 are said to be essentially identical if they stand in that relation to each other. Here's an example. So let D1 and D2 be derivations in cut-free SN4. Then, by the first clause in the previous definition, D1 is identical with this derivation where we apply an interaction rule. and D2 is identical with this derivation where we just add one inferential step by applying an interaction. Then by the second clause of the definition, these two derivations are identical. So we have now here's a conclusion sequence of proof and here a refutation, but what we have above are identical derivations. By the first clause, these two derivations are identical, and then by transitivity we obtain what we want, namely that this proof of not A and not B is identical with this proof of the negation of A or B. And now comes the definition of synonymy. So two formulas A and B are synonymous with respect to cut-free S and 4. If and only if for all finite multisets delta and gamma, these two conditions are satisfied. So for every derivation D of gamma colon delta arrow plus A, there's a derivation D prime of gamma colon delta arrow plus B, which are identical. And for every derivation D of gamma colon delta arrow plus B, there's a derivation D prime of gamma colon delta plus A, with D being identical with D prime. And similarly for refutations or disputes. Good. Okay. So now we have the notion of synonymy that is based on identifying derivations in cut-free S and 4. And then we can observe, for instance, that the following pairs of formulas are synonymous with respect to our sequent calculus. So A and not A and B and not A or not B, and A or B and the negation of not A and not B. Good. But maybe you recall this connective of strong equivalence. So two formulas A and B are strongly equivalent in cut-free S and 4 if the statement that they are strongly equivalent is provable, and we can easily see that this is the case just in case we can prove that we have a proof of B from A and a proof of A from B, and we have a disproof of B from A and a disproof of A. Good. And now one may wonder, no, the question comes a little bit later. So first we can observe that if A and B are synonymous, then A and B are strongly equivalent. This is already useful because we can derive that the following pairs of formulas are not synonymous with respect to our sequent calculus S and 4. Why? Well, the negation of A implies B and A and not B, they are not strongly equivalent. But also A implies B implies B, and B implies B implies A implies A. These formulas fail to be synonymous because they are not strongly equivalent. So this observation is useful. But now one may wonder whether two formulas are synonymous in cut-free S and 4 just in case they are strongly equivalent. I'm not sure whether this would be a confirming or reassuring result. In any case, strong equivalence in S and 4 does not imply synonymy in cut-free S and 4. So maybe this is even surprising. So here's a counterexample. These two formulas are strongly equivalent, but there's a combinatorial argument showing that they are not synonymous. So it's not that simple that synonymy coincides with provable strong equivalence. Good. How much time is left? Still some? Okay, then I will continue. So now one may wonder, okay, so this idea of defining synonymy in proof-theoretic semantics it's really developed from this idea of having two kinds of derivations, proofs and disproofs, and it is inspired by this proof-disproof interpretation of the intersynesthetic connectives due to Lopez Escobar. Can one continue from there to some to others slightly more general settings? Yes, one can. There's a certain gap in the system of rules for SN4. Why? There's no connective that stands to disjunction with respect to disproofs, as conjunction stands to implication with respect to proofs. And if we want to close this gap, this calls for adding to the language of Nelson's four-weighted logic a connective that is in a certain sense dual to implication, namely co-implication. The co-implication connective which I considered in a series of papers. So we can then add roots for this co-implication connectives to begin with to our standard sequence calculus for N4. So then the idea is if from the assumption that A is false, we can derive that B is false, then that's not the case that A co-implies B. So this is in a sense, of dualizing implication. Good. Then we can use the same method we used to move from GN4 to SN4 in order to go from the extension of GN4 by co-implication to an extension of SN4 by co-implication. Yes. So from A as a counter assumption, we derive that B is false. We have a disproof of B. Then from gamma as a set of counter assumptions, and that as a set of assumptions, we can go to disproof of A co-implies B. Good. So we can consider the addition of this co-implication to the language of N4. If we add the sequence rules we've just seen to GN4, we obtain the system GN4 with co-implication. And if we add these sequence rules to SN4, we obtain SN4 with co-implication. We can then also consider the result of dropping the strong negation. And if we do that, we obtain logic which we obtain a sequence calculus which we may call S2 intersynesthetic logic, because it is a sequence calculus for the system of two intersynesthetic logic, where you have implication and co-implication, but you do not have the strong negation. Yeah. You do have two negations in this two intersynesthetic logic, because you can define the truth constant as P implies P for some proposition variable P, the falsity constant as P co-implies P. And if you have these two constants, then you can define two negations. The intersynesthetic negation as A implies absurdity, and the co-negation as A excludes the truth, A co-implies P. Good. And then, if we want to apply the same ideas as before, then the question is whether there are interaction rules for this two intersynesthetic logic, and this sequence calculus for two intersynesthetic logic, where you do not have the strong negation, which played an essential role in identifying derivations in SN4. So you don't have it anymore. But you nevertheless can define interaction rules that allow for an identification of proofs and disproofs of distinct formulas from the language of two intersynesthetic logic, where you have the two negations, intersynesthetic negation and co-negation, no strong negation, but you nevertheless want to identify derivations. So are there suitable interaction rules that are such that their application does not have an effect on the identity of derivations? Yes. But the connection between proofs and disproofs is now not established by the single strong negation as in Nelson's case, but by a combination of the two defined negations. So that we obtain these interaction rules. And they are derivable in the sequent calculus for two-meter syllogistic logic. And these interaction rules are sort of nice because they do not violate the subformular property, but the inverted interaction rules are also derivable in the sequent calculus for two-meter syllogistic logic with the help of the cut rules. And they are subformular property spoiling. However, not only the identity axioms are provable in our sequence systems for the logic without strong negation but with implication and co-implication, but the inverse interaction rules are admissible. So what we can do is now we can define identity between derivations also in the case of cut-free S2-end. So we can basically use the same definition as before. We work with cut-free S2-end, and let me jump back to the definition. So the only difference is that we replace SN4 by S2-end. So we can basically use the same definition. Of course, we are then referring to other interaction rules than in this case. But the same approach can be applied. So yes. So let me make some concluding remarks. So as I said, there's a consensus that synonymy implies sameness of denotation. So if we think of derivation trees from the perspective of modern theoretic semantics, then it's natural to wonder about their denotation. What do derivations refer to? And maybe also we want to know what do they express? What is their Phrygian reference and what is their Phrygian sense? What is their mode of presentation? So whatever the denotation and the sense of derivations is, I think it's clear that identical derivations ought to have the same sense and therefore also the same denotation. This is Frege's idea, at least, that sense determines denotation. But there's not much work on the sense of derivations, so I'm aware of only two papers on this subject. And if we want to make sure that two derivation trees are co-referential, if they are coded by co-referential uniquely typed lambda terms, then a two-sorted type lambda calculus is needed because we have two kinds of derivations, proofs and refutations. And as for a connexo variant of this biintersynistic logic, such a two-sorted type lambda calculus has been presented by me in a paper. And okay, so then we are working with two sorts of type variables, proof variables, which we may decorate with a plus, and disproof variables, which we may decorate with a minus. And we also need the usual term-forming operations and new term-forming operations for creating positive terms and negative terms. And then we can take the interaction rules of our subformula calculus for N4, for instance, to give rise to a term assignment rules. And this is now really very, very tentative and sketchy. And then we may note that, well, these derivations are identical. If we encode the two identical derivations by type terms, we obtain these derivations. And then we need a semantics for the two-sorted type lambda calculus such that this equation would have to be valid. But this has not yet been worked out. So this is very programmatic. Well, I conjecture that there is a sound and complete semantics for the two-sorted type lambda calculus for which which for every formula A makes use of a pair of domains. So we would also have to distinguish between positive and negative domains because we have two sorts of type of lambda terms. But this is rather sketchy and the end of my talk. Thank you very much.